In this lesson, we'll look at some of the different polar graphs. So if we have a polar equation where the input will be the theta, and then the output will be the r. And just like normal, if we're not sure how to graph something, we'll always start with a table. So we'll just take these different angles and plug them into the equation, and then plot the polar points. So if we have an angle of 0, the cosine of 0 is 1. So here we're going to have -3 plus 2. So that will be -1. And then cosine of pi over 2 is going to be 0. So -3 plus 0, we're just going to have -3. And then cosine of pi is -1. So 2 times -1, -2. So we've got -3 plus -2, -5. And then for 3 pi over 2, the cosine is 0. So we'll just have the -3. So then we have to plot these polar points, and just remember that these are polar points. So we want to look at the theta first. And so we're going to go an angle of 0, which is straight to the right, coterminal with an angle of 2 pi. But then the r is negative. Remember, if r is negative, it tells you to go the opposite direction. So instead of going straight right, we're going to go straight left. And so the point is going to be over there. And then pi over 2 would be straight up, but because the r is negative, it's going to flip us backwards. So we're going to be in the opposite direction. And so we're going to be straight down. And then here's where some of these points can confuse people a little bit, because we go an angle of pi, which is already left, which is already the negative direction. And so sometimes people see that -5 and they think, oh, -5, that's right here, that's the right place. But remember, this is r being negative, telling us to go the opposite direction. So we go an angle of pi, and then a -r tells us to go the opposite direction across the origin. So we're actually going to be over here at an x of +5. We're going to be over on the right. Same thing here with 3 pi over 2. The angle of 3 pi over 2 is straight down, which you're used to thinking of as negative. But that -r tells you go the opposite direction. And so you're going to flip back here, go an angle of 3 pi over 2 straight down, and then -r opposite direction. Now you're straight up. And so you have this point here. Okay, and then these polar graphs are all going to be at least somewhat circular. Again, polar is a circular system of doing points. There's actually a name for some of these graphs. This is called a limaçon. It's French. And these graphs are actually the sound field for some different microphones. Sound engineers designing microphones will use some of these different graphs. But you don't need to know any of that. Just graph these points and draw something semicircular around it, and that's enough for us. Now, these down here are not just going to be somewhat circular, they're actually going to be circles. So for example, right here, this says no matter what the angle is, go a distance of 3. Well, that's actually the definition of a circle. Circle is the set of all points, a fixed distance from some center. So if you go from the origin a distance of 3 everywhere, you're just going to have a circle with its center at the origin and a radius of 3. That's it. All right. These are actually going to be circles as well. And I put kind of all 4 different types that we'll see. You can kind of just start to get to know these circles to be able to sketch them really quickly. They are some of the more common ones you might see in AP Calculus, but you can also make a table, but you'll see that the table doesn't really give you a whole lot. That's why sometimes we just recommend that you know these as circles. So for example, number 2 here, if we did the table, sine of 0 is 0 and sine of pi is 0. And then sine of pi over 2 is 1. So 2 times 1 is 2. Sine of 3 pi over 2 is -1. So we have -2 here. So if you plot these points, whenever your r is 0, it doesn't matter how you rotate. If the distance you're going from the origin is 0, these points with an r of 0, you're just going to be stuck at the origin. You're not going to be going anywhere. So both of these points are in the same place right there. And then if we rotate pi over 2 and go a distance of 2, straight up will be right there. And then 3 pi over 2 is straight down, but then that -r flips us back up. And so this point actually matches this point as well. So if you make a table, all you're going to see is those 2 points. You're not really necessarily going to know what's going on with this graph. So that's part of why we do recommend you just know these are circles. If all you have is a number in front of the sine or the cosine, and that's it, those will be circles. And so these points are the endpoints of the diameter right there. If you want to try to sketch a more accurate circle, if this is the diameter is 2, that means the radius is 1. So this right here would be the center. So you could go a distance of 1 off to the sides there as well. And then that could help you draw something that looks a little bit more like a circle right there. And so for all these other ones, if you wanted to, you can make a table again to see where the endpoints of the diameter are, to see where the circle is. But it's fairly easy to tell what kind of circles they are. So notice here, this was sine in the equation, and we're used to sine going with y, like on the unit circle, sine is the y coordinate. And so the circle here was on the y-axis. Well, here, if we have cosine instead of sine, cosine goes with x. So cosine is going to be on the x-axis. And this number out front, this 2, is how far out we can go. We can go out to a distance of 2. So we're going to just have a circle on the x-axis now with that diameter of 2. And so we could sketch that circle. Again, if you want to make a table to find these 2 points, you can. It's just then from those 2 points, you would need to know that that's a circle. And then these, because we had positive coefficients out front, the circle went up and to the right. If we had a negative out front, just instead of going up on this one, we're going to go down. And so the circle will be here. Again, sine is on the y-axis, positive is up on the y-axis, negative is down on the y-axis. And then here we've got cosine. Cosine is going to be on the x-axis, and because it's negative, we'll go left. Again, that 2 tells us how far we can go from the origin. And so there we go. So that's circles. Another type of polar graph you can get some really interesting shapes from polar graphs, actually. Another one you can get is kind of flowers. So we call them petal graphs. So if you look at r equals 4 sine 7 theta, I should mention, by the way, we can do these in our calculator. Maybe I'll go back to this first one just to show you here. There is a polar mode in your calculator. If you go to mode, and we've looked at function, we've looked at parametric. This third one here, that pol is for polar. So if you change your mode to polar there, when you hit your y equals button, it's not going to be a y equals anymore. Now it's going to be an r equals. And so we can type in -3 plus 2 cosine. And then to get the theta, again, this button next to alpha, when we were in function mode, it gave us x. When we're in parametric mode, it gave us t. Now that we're in polar mode, it'll give us this theta right here. And so you can either zoom 6, or if you want to really see things, like if something's a circle and you want to see for sure it's a circle, your calculator has the zoom square feature to help you see it a little bit more exactly as it should look. But polar graphs you can do in your calculator. And so if we did graph this one right here, this is how it would look. It's a petal graph. And so what we found in AP Calculus, though, is that students don't necessarily need to know that this equation gives them this graph. Usually either the graph is given or you have your graphing calculator. What you need to be able to do is identify different values of theta that correspond to different points. So some of the important points that we might look at would be a tip of the petal. So if we were trying to find what value of theta gives us this point right here, well, what's important to notice that the tip of the petal, that's the furthest out you went. That's the biggest R you have, the maximum distance from the origin. And we actually know what that is. If we look at the equation, we know what this maximum distance from the origin is. If you remember sine, all sine graphs had a maximum value. When we graphed sine, the biggest it could be was 1. If you remember on the yellow sheets, the graph of sine just bounced back and forth between -1 and 1. It had an amplitude. So if it's just sine, the biggest it can be is 1. Well, this 7 inside the function is not going to change that. The 7 would change the period. So I'm talking about if we thought about this as maybe a rectangular graph, y equals 4 sine 7x. If we thought about this, the 7 would change the period. It's the 4 that would change the amplitude, that would change the maximum value we could have. We would have an amplitude of 4. So that means that the maximum R we can have here is 4. So we know for the tip of a pedal, R has to equal 4. So that means for part A, if we want to find the theta, we know we're trying to find what theta makes the R be 4. So we can just plug in 4 for R. We can say, when does this thing actually equal 4? And then just solve that equation. So then we can divide both sides by 4. And we want to know, when does sine of 7 theta equal 1? And the way that we solved those was we kind of ignored the 7 theta for a second. Sometimes we even looked at, we could do a u substitution if we wanted to. And we just looked at, when is sine 1? What kind of angle gives us a sine of 1? And of course, that's pi over 2. And so we're thinking about the angle pi over 2 here. That's when sine is 1. But that's not theta. That's not our final answer, because that tells us what's inside right here has to be pi over 2. If I replace my finger right there with pi over 2, then I'm going to get 1. If what's behind my finger right here, sine of my finger, sine of pi over 2 is 1, then it'll work out. That's what we want. So that means 7 theta has to equal pi over 2. So then we divide both sides by 7. You might be somewhat familiar with those now. You might already know how that's going to turn out. Otherwise, of course, we can multiply by the reciprocal. And so we get pi over 14 as our final answer. Right? So that's finding the tip of the pedal. We look at what the maximum R is, kind of like the amplitude when we were graphing these as regular rectangular equations. It's just going to be this number, this coefficient in front of the sine or the cosine. That's the biggest that we can be. All right, so now how about a point at the origin? What kind of angle might give us a point just right in the center right there? Well, we looked at this a minute ago, what it means in polar to be at the origin. So we know in regular rectangular in x and y, the origin means both x and y are 0. How about polar? So polar is r and theta. Well, to be at the origin, it doesn't matter how you rotate it. You can rotate any way you want. Being at the origin just means that your distance is 0. It means you didn't actually go anywhere, any distance from the origin. So for polar, the origin is r equals 0. So this time, instead of setting the equation equal to 4, now we'll set the equation equal to 0. We'll look for 4 sine 7 theta to equal 0. So we'll divide both sides by 4. So we want sine of 7 theta to equal 0. Again, we'll ignore that 7 theta for a minute, and we'll think about, well, when would sine be 0? So if we think about the unit circle, we want the y-coordinate to be 0. And so the y-coordinate being 0, that's either 0 or pi. But notice we just want the first or the smallest value. There's always an infinite number of angles that solve anything. We just want the first or the smallest one. And so we'll just say 0. Now that is what 7 theta equals 0, or what 7 theta equals. But if 7 theta equals 0, then theta equals 0 as well. So to find when it's at the origin, you just set the equation equal to 0, you make r be 0, and to find the tip of the pedal, you set the equation equal to whatever this leading coefficient is in the equation.